All right, today we're going to take a journey, not to some far-off place, but deep, deep inside the tech you use every single day. We're going to explore the invisible, lightning-fast city that lives on a tiny sliver of silicon, your processor.
I want you to picture a huge, bustling metropolis, just humming with activity. And now, shrink it down to the size of your thumbnail. That's pretty much what a modern system on a chip, or SoC, is. It's not just one thing, it's a whole collection of super specialized components, let's call them districts, that are all working together. And each one has a really critical job to do.
And we can actually map these parts to our city idea pretty easily. The CPU, that's your central business district. The downtown core, making all the big decisions and asking for information. The system memory, or your RAM, that's like a grand library holding all the data the city might need at a moment's notice. Your GPU is the high-tech movie studio, rendering all the amazing graphics you see on screen. And things like USB and Wi-Fi, those are the busy shipping docks bringing information into and out of our little city.
But here's the catch. With all these different districts constantly needing to chat with each other, you run into a huge problem. How do you manage all that back and forth without it just turning into total chaos? And that brings us to the on-chip traffic jam.
I mean, just think about it for a second. What if the movie studio, the business district, and the shipping docks all tried to access the library at the exact same time, on the same road? You'd get instant gridlock, a total standstill. No information would move, and your device would get super slow or, just freeze up completely. This is one of the biggest challenges in designing a chip.
So, how did engineers get around this? Well, they built an incredibly sophisticated, high-speed road system. And the blueprint for that system is a protocol called AMBA ASIC. For our purposes, let's just think of it as the city's main information superhighway.
So the AXI protocol is basically the official rulebook for on-chip traffic. It defines this high-performance interconnect, that's the technical name for our highway system, that links up all those districts. The whole thing is designed from the ground up for massive bandwidth and super low latency. In other words, it's built for pure speed and efficiency.
So how does this AXI highway actually prevent traffic jams? Well, let's take reading data, like when the CPU needs something from memory. It uses two separate dedicated lanes. First, a request zips out on the address lane. It's kind of like sending a courier to a specific shelf in the library. Then the information comes back on a totally separate data lane. This simple separation means you never have any head-on collisions.
Writing data is just as organized, but it's even more reliable. You still got an address lane to say where the data is going and a data lane for the data itself. But AXI adds this brilliant third lane, a response lane. This acts just like a signed delivery confirmation, letting the sender know, yep, your package arrived safely. This whole system of separate channels is really what makes the AXI protocol so powerful.
Having separate lanes is a great start, for sure. But a truly smart highway needs some intelligent traffic rules to keep things flowing smoothly. So let's talk about the AXI rules of the road.
Okay, the absolute bedrock of all AXI communication is something called a handshake. It's a really simple but totally foolproof agreement that has to happen before any information changes hands. It makes sure that data is only sent when the sender is actually ready to send it and the receiver is actually ready to get it. You can think of it like a smart traffic light. The sender puts up a flag that says, "My information is valid." At the same time, the receiver puts up a flag that says, "I am ready to receive." The transfer, the green light, only happens when both of those flags are up. The official spec says it perfectly. Transfer occurs only when both the valid and ready signals are high. This simple rule means data basically never gets lost or messed up on its way.
The next big rule is all about being as efficient as possible. Instead of sending single cars down the highway one by one, which would be a huge waste of time, Async organizes data into these neat little convoys, which the protocol calls bursts, and this is absolutely key to its high performance.
And you can really see the difference it makes here. Without bursts, you have to send a new address for every single piece of data you want. It's slow and it totally clogs up the address lane. But with AXI bursts, you just send the start address one time and then a whole convoy of data. We're talking up to 256 pieces in some versions, just follows right behind in a nice organized stream. It's an unbelievably effective way to move big chunks of data with almost no extra work. So, we've talked about the lanes and the rules, and we've gotten a little technical. But why does any of this actually matter to you? Let's connect this invisible highway inside your processor to the actual experience you have with your devices every day.
Seriously, every single time you multitask on your phone or your computer, you are seeing the AXI protocol do its thing. Because this system is so good at moving data around, all the different parts spend less time waiting and more time working. And that doesn't just make your device feel snappy and fast, it actually helps with battery life too. It's this silent, invisible traffic management that lets your GPU render a crazy game while your CPU runs your apps, all at the same time, without a hint of gridlock.
So, when you boil it all down, the secret to our fast city on a chip really comes down to three key ideas. First, those dedicated lanes that prevent traffic jams. Second, the smart handshake that guarantees every piece of data is delivered safely. And third, those super efficient data convoys, or bursts, that move massive amounts of information at incredible speeds.
The AXI protocol has been absolutely fundamental to chip design for years now. But as our technology demands more and more AI, more VR, more data, the digital cities inside our devices are just going to get bigger and way more complex. Which kind of leaves us with one final thought. What kind of incredible new information superhighways are engineers going to have to invent next?